Okay, we are now ready to use all of these various filling rules to show how electrons arrange themselves in all of the atoms in the periodic table. So we'll first just write the order of the orbitals in order of increasing energy. I'm going to write those across here from lowest energy to highest energy. And they start at the lowest at 1s, 2s, 2p, 3s, 3p, 4s comes before 3d, then you have 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. These are the orbitals in order from low energy to high energy. And let's say we want to write the electronic configuration, or how the electrons arrange themselves in the hydrogen atom. Well, the hydrogen atom just has one electron, so there's only one electron we're going to need to fill in. So what we'll do for the hydrogen atom is we'll write the first orbital, which is a 1s orbital. We'll write it like this. And then there's one electron that we need to stick in, and so we'll just put that electron in. I usually just do it spin up first. And we're done. It's that simple. Now we can look at all of the quantum numbers for this particular electron. We see that n is 1 because it's a 1s. L is 0 because it's an s orbital. M sub L has to be 0. That's true for all s orbitals. And its spin is plus half. So M sub s is plus half. Say we want to do a helium atom. In this case, we're going to need to fill in 2 electrons because a neutral atom of helium has 2 electrons. And so we're once again going to need to use our 1s electron. That's where we're going to start. And we can put the first electron into our helium atom as such. The second electron, we've got to put 2 in because it's helium. That's going to need to have one of the quantum numbers different. So this first electron has these 4 quantum numbers. The second electron cannot have the same 4 quantum numbers. It can have 3 of them the same, which it does. N is 1, L is 0, M sub L is 0. But we're going to have to stick that second electron in with a different spin. So this one's going to have negative half. And in that case, we're done. We should also notice that the 1s orbital at this point is full. It can't accept any more electrons, because if I were to stick another electron into this particular orbital, it would violate the Pauli exclusion principle. Another electron in here, we'd have to give it the same 4 quantum numbers. And that's going to be important when we get to lithium. We'll note that lithium has 3 electrons. And so we'll fill them just like before. We have the 1s orbital. And in this case, we fill the first 2 just like we did before. But now that third electron is going to have to go into a different orbital. So we've used up the 1s orbital. We're now going to have to start filling the next highest energy level orbital, which is the 2s. And we're going to stick an electron in like this. Now these 3 ways of drawing what we call the electronic configurations for the electrons in the atoms, these are called orbital box notation, in which each of these lines sort of represents a box into which the electrons go. So the orbitals are viewed sort of as boxes into which the electrons go. There's another type of notation that's sometimes used. It's called Spdf notation. And when doing this, what one does, for example, for this particular electron configuration, we'd write 1s, and there's 1 electron in the 1s for hydrogen. So this would be the Spdf notation for the electronic configuration of hydrogen. For helium, we'd write it like this, 1s2, because there's 2 electrons in the 1s for helium. And for lithium, Spdf notation, we'd write it like this. 1s2, because there's 2 electrons in the 1s. 2s1, because there's 1 electron in the 2s. I hope I said 2 electrons in the 1s. 2 electrons in the 1s, 1 electron in the 2s. All right, let's go up to the next atom, which would be beryllium. So if we look at beryllium, we notice that we're going to have to fill 4 electrons for beryllium. So we'll begin. 1s, we're going to put 2 electrons in to fill that. Once we've filled up the 1s, we're going to move up to the 2s, and we're going to stick 1 electron spin up, 1 electron spin down, and we've written the orbital box notation for a beryllium atom. We can also write the Spdf notation as 1s2, 2s2. Okay, now we can move up to, let's go ahead and skip boron. We'll go all the way to oxygen. So we're going to put 8 electrons in for oxygen. So let's see, oxygen. We got to put 8 electrons in, so we're going to start with the 1s. And of course, we're going to put 2 electrons in to the 1s. That's now full. We used up 2 of the 8 electrons. We got to now go to the 2s, and we put 2 electrons in there. And now we filled up the 2s orbital. So now we've got to go to the 2p. Now with the 2p, things are a little different. In a p subshell, you should recognize that there are going to be 3 orbitals. Now that's because the value of m sub L for any s electron is always going to be 0. And so you only get 1 orbital for an s subshell. For a p subshell, m sub L can be -1, 0, or +1. So you always get 3 orbitals in a 2p subshell. Now back to oxygen, we have 8 electrons that we want to stick in our oxygen, and we've used up 4. That means there's 4 more we're going to stick in here. So we're going to start putting the 4 electrons into the 2p subshell, and we're going to do it one at a time, and we're going to remember that we're going to, I'd like to just go spin up first. The second electron, remember we want to stick it in another orbital. We don't want to stick it in the same orbital if we don't have to. And we're going to align the spins. So let's see, how many electrons have I had so far? 1, 2, 3, 4, 5, 6. I got to do 8. I got to put another one in. This will be my 7th electron. I'm going to stick it in a different orbital spin up. So now there's 7. I've got to put 1 more in. I'm just going to stick it in here, spin down. This would be the orbital box notation for the electronic configuration for oxygen. We'd write it like this. In Spdf notation, I would write this as 1s2, because there's 2 electrons in the 1s, 2s2, because there's 2 electrons in the 2s, and 2p, 1, 2, 3, 4. So this would be the Spdf notation for the electronic configuration of oxygen. Okay, let's try chlorine. We're going to go all the way down here to number 17. So I've got to stick 17 electrons in. I'm going to keep this down here so I can sort of keep track of my orbitals that I'm going to fill in terms of energy. And I'm going to write, let's see, 1s is first, and then 2s, and then 2p, but for a 2p I'm going to use 3 orbitals. Remember, a 2p subshell gets 3, and then 3s, and 3p. 1, 2, 3 for a 3p, right? S's get 1 orbital, p's get 3 orbitals. And I kind of know to quit here. And how do I know how to quit here? I'd like to show you this. I'd actually like to show you how I kind of know where to stop. Now, if you look here, I'm going to just sort of use the periodic table sort of as I fill these particular electrons going all the way up to chlorine. So I'm going to start here with hydrogen, and I'd put 1 electron in for hydrogen, spin up, and I'm going to stick a 2nd electron here for helium, spin down. And notice I'm in the first period of the periodic table, and there's only 2 atoms in the first period of the periodic table. I've put 2 electrons into the 1s. I've run out of the period, and I've run out of room in the 1s. That's no coincidence. When I get to lithium, I have to move down to the next period, and to fill the electron, I have to move up to the next orbital. I'm now in the second period, and I'm in the second shell. I'm now going to fill in an electron for lithium, and I'm going to fill in an electron for beryllium. Of course, I got to go spin down here. And notice, I've run out of the 2s, and I've also run out of sort of this 2-column space on the periodic table. I'm now going to skip across to this section of the periodic table. Look, there's 1, 2, 3, 4, 5, 6 atoms in this portion of the periodic table. And I have 3 orbitals into which 2 electrons apiece can go. That means I can put 6 electrons here. Hey, that's no coincidence. 1, 2, 3, 4, 5, 6. Watch this. I'll put an electron in for boron in the 2p region. I'm going to put 1 in for carbon. Notice I'm following Hund's rule. I'm going to put 1 in for nitrogen. So I'm right here. Now I'm going to stick 1 in for oxygen. Now I'm going to stick 1 in for fluorine. And now I'm going to stick 1 in for neon. And look at that. I've run out of this portion of the periodic table. I've come to the end of the second period, and I've run out of the 2p subshell. And now I'm going to need to fill an electron for sodium. I'm going to have to move down 1 level, and I'm going to have to move up to the 3rd shell. And I'm in this 2-column space of the periodic table, and I'm in the 3s. It's almost as if this portion of the periodic table, these 2 columns here, it sort of corresponds to the S subshell, doesn't it? And I'm wondering if this portion of the periodic table here, that fits 6 atoms, I wonder if this corresponds to P subshells. Let's just see. Nevertheless, the 11th electron is going to go into this 3s. For magnesium, it's going to be the opposite spin. I've run out of this portion, the sort of S columns of the periodic table. I'm now going to jump across to these P columns of the periodic table, and I'll start filling in an electron here for aluminum, another one for silicon, another one for phosphorus. So notice I put the electrons in opposite orbitals, in different orbitals with their spins aligned. Now when I get to sulfur, they're going to have to start pairing up, and here's chlorine. And now I've drawn the orbital box notation for a chlorine atom. And if I want to write the Spdf notation for the chlorine atom, I would write it as 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. So these would both be ways to write the electronic configuration for the way the electrons exist in a chlorine atom.